Hello and welcome. We're going to talk about finding, importing, and data and doing all that kind of stuff. My name is Dr. Harmon. I'm the program head here at GIS, and I'm your radio voice in today's lecture video. And we're going to talk about GIS data because they are different than other data. How are they different? Well, shall I count the ways? A lot of times, GIS data, spatial data, are very large. If you think about it, if you have a raster data set for, like, say, the state of Virginia, and it has a 30-meter resolution, that means that for every, starting at the top right or top left corner of Virginia, every 30 meters that you move left to right and up and down, you create a nice little square and you get a measurement like elevation. And if you think about the size of the state of Virginia and you think about how many of those little squares there are, you can easily see how quite often these data sets are, as we say in the professional world, freaking huge. Um, Often, unlike a lot of data sets, spatial data tends to be shared by multiple users. It's not uncommon in some enterprise GIS environments for one data set to be accessed multiple times by lots and lots of people doing lots and lots of various different things with it. We also find that GIS and spatial data in general come from lots of sources, and there's lots of different file types. In the little box that you see there on the right, you see all those files that say buildings. One of the things that we never ever do in GIS is try to copy and move stuff using things like Windows Explorer. GIS files are special. All those 1, 2, 3, 4, 5, 6, 7 files that you see there, they all are part of one simple feature, a shapefile called buildings. That shapefile has all those different components, 7 different component files that make it up. When you try to go into something like, for example, Windows Explorer, you see all 7 of those files. If you miss one, the shapefile will not function properly. If you go into our catalog to move things around, which is basically the same sort of program as Windows Explorer, the big difference is it knows that this is a shapefile. It knows there's multiple components, and when you look in catalog, you only see one file called buildings.shp. And when you move it, it copies and moves all these things as well, so that you don't have to worry about it. Sometimes data is local, in other words, it's right on your workstation, and sometimes it's served, it's on a server where you're working from the server. That is a difficult ask because to do GIS across the internet is never easy. And so typically, even if it's served, we're going to copy it and download it to our local location and work on it there, and then when we're done, upload it back to the server in some format. A lot of times, spatial data don't always follow the latest file conventions. Things change, people don't follow rules, things happen. And what this ultimately leads to is the formats that you have to deal with, because some come from having trouble speaking here. Some come from proprietary software or use outdated or outmoded file formats. You end up with a situation where figuring out what format something is in and whether you can use it or not can become complicated. So how do we organize GIS data? There's lots of different ways. I'm going to give you just the really basic stuff here and then give you a couple helpful hints that I find work well for me. We want to use organized folders with our geospatial data. You need to always be aware of where you're saving things. The software has this habit of putting everything in this default location, and that is not a good place, because if you don't specifically give a file a name when you're using tools that generate new files, it will call things stuff like raster 1 and raster 2, And if you're using just a single location like this that doesn't have any way of dividing it up, then later you need to go back and find raster 1 or raster 2. Raster 1 or raster 2 is lost in a sea of data of unknown origin, and that is not a good thing. So know where you're saving it, and make sure that where you're saving it is not just the default location for everything. Next up is how you name files. You want to use descriptive names, things like snail habitat as opposed to raster calc 1. Now raster calc 1 might be a complex calculation from multiple data sets that leads you to the ability or capacity to map out snail habitat, and that's wonderful. Don't call it raster calc 1, call it snail habitat. Couple of my personal hints. Start off like this. Figure out where you're going to put your GIS work and create a general folder overall to put that in. So don't work off your desktop. You can create a folder on your desktop and put things in that. That's great. Now, once you've created this folder that you're working from, in that folder, make a download, make a working, and make a final folder. And this is how this should go. When you download data, download it into your download folder. Once you download it into the download folder, if it needs extracting, go into that folder and extract it into the same folder. Once all that's done, you can then open up your GIS, import your data from your downloads location, set your default to your working folder, and then as you're making things and doing things, it goes into the working folder. In the working folder, create folders for each project. Now I take it a step further. You can get away with just that. I like a final folder, and that final folder would have folders for each project. And basically, once I figure out how to do something, I like to then go into the final folder, create a new folder for that project, go back to my downloads, download all the information I have to have into a brand new folder, and then go through the process of creating all my data layers again, but I do it in a cleaner, more straightforward fashion. I've already debugged everything, and I know all the problems and I know all the fixes, and that allows me to have a really neat, clean final data set without having to go back and eliminate and clean up a lot of cluster and clutter. So Mary Beth Price, the author of the textbook, which, by the way, is, I think, one of the most awesomest textbooks ever, even if awesomest isn't a word. We're going to use folders. In this example, C drive, they say not to put it on the desktop. Now, this can be a problem sometimes because some computers may not, in a college environment, let you have write access to a C drive. And the desktop can be a problem because it's not necessarily in your user folder, and it can be a little bit tricky to find, but we can work on that. Figuring out how to find your folders in GIS is not a trivial thing, and you will lose more data than you'll find for a while. But we'll help you with that, and over time you'll get good at it. But the main thing is you have to develop some sort of an organizational system that works for you and then use it. Simply saying, I don't know where it went, Dr. Harmon, it doesn't fly with me. If you don't know where it went, you got two options. Look for it, because I'm not going to look for it for you, or do it again. Now, you're going to think, oh, I'm not going to do it again, I'm going to look for it. Guess what? It's almost always faster to do it again than it is to look for it. So, just FYI, helpful hint. It's usually faster to do it over than it is to spend 20 minutes trying to figure out what folder you put it in. Just do it over and know where you put it the second time. Again, put downloads in separate folders when you're putting your data together. This is some basic stuff. Like I said, I went over it a little bit beforehand. Price is going over it again here. You need to take these things to heart. It will only make it easier for you if you do this. Naming conventions. There are certain things that make the GIS hair on the back of a GIS professional's neck stand up and shout, and that is really improper naming of folders. First off, never use spaces in folder names. If you have a space, it can create all kinds of problems. And it's not just in the GIS file. You can put it in the folder and it creates problems. Never, ever, ever use spaces. And so some things you can get away with in some situations and some things you can't. I like to just adopt these basic premises for everything I do in GIS, and I won't create a folder or a file unless it meets these criteria. And these criteria are simple. Never use a space. Use letters and numbers only, and the underscore symbol if you need to space things apart. Keep your folder names or your file names short, 8 to 15 characters. They say it's not really a requirement, but it's good practice. If your file length gets too long, it can be a problem. A couple other things you want to remember. Don't start file or folder names with a number, like 6 alpha or something. Alpha 6 would be okay, but 6 alpha, that can create some issues. So follow these basic conventions and your file should work fine without giving you any problems. So important. Windows permits spaces, GIS does not. They're a bad idea, so just get used to not doing it. What will happen is they may work for some things, and then you'll try to run a tool or something and it comes up to a space, and it's not always the space that you think. That's one of the benefits of putting your folders and stuff off a C drive as opposed to your desktop, is if somewhere between the desktop and your folder there's a folder that has a space in it, that can cause things to malfunction and shut down. So just as a practice, starting right now, get used to not using spaces or dashes or any kind of special symbols. Numbers, letters, underscore. That's it. Don't start with a number. File extensions. This is a way that you can tell what the file is. There are 3 to 4 letter codes that end up at the end of the file. ArcGIS, when you create stuff, will automatically add the file code that goes along with the type that you're creating. Things like DOC, DOCX, XSL, XMD, PNG, JPEG, TIFFs, they're all different designations, and as you start using the software, as you start looking for data, you'll start to recognize what these things are and understand docs is like a Word thing. XLS, these are spreadsheets. MXDs is a map document. A TIFF is a uncompressed photo or image. A PNG is another type of image. A JPEG is a highly compressed image. These things are things you'll learn over time, not something you need to fret about. Change your computer settings to make these things visible. It will help you when you're trying to find data. It's very helpful when you're downloading and importing data sets, because if you really need an image and the thing that you're downloading is a doc or an XL, you know that's not going to be what you want. So speaking of this, how do we find data? Really good question. There's lots of data out there. ArcGIS Online has a ton of stuff. The thing is, not all of it is downloadable. Some of it is. You can go up into your menus up there where you're adding data and that sort of stuff, and there's an option to not just add data from a folder, but you can add things from ArcGIS, ArcGIS Online. Yawned again, sorry. You can find a lot of cool stuff there. Some of it's good, some of it's not good. Some of it's downloadable, some of it's not downloadable. The other alternatives are various state and federal government sites, and some of these work awesome, and some are just the most horrendous, difficult, horrible, deplorable, unmanageable, unwieldable, just black holes of progress, hope, and joy. In other words, they suck the very goodness out of your soul, because they're really difficult to use. There's GIS clearinghouses. They store all kinds of stuff, even metadata, and some of those are just like those state and federal sites. They're awesome, and some are just like the other state and federal sites where they make you want to gouge your eyes out with sticks. Same for university and research organizations. So some's great, some's worthless. What will separate you from the GIS masses is the ability to find good sources of data and then acquire it. And the first mistake people make is they read the title of a data set and they say, "Ooh, that's exactly what I want," and they download it, and that's the end of it. And then 3 months later, they look at it as they're getting ready to do the project, only to find out that it was absolutely nothing like what they thought it was based on the title. As a rule of thumb, when you think you found data that you need, download it, open it, look at it, and confirm what is there. If you don't understand what's there, it's the same as nothing being there. You have to figure out what is there. You have to read the metadata. You have to sometimes Google it and figure out what some of the codes mean, because it might have a standard accepted universal way of identifying stuff. And if you do a little Google work, you can come up with what that means, and then figure out that the data set you have is exactly what you're looking for, or completely and utterly worthless. You have to spend the time to figure these things out. Here's an example. This is the data.gov site. It is one of my least favorite. You can also just search. Turns out this actually works pretty decent. You put in a topic like Mount St. Helens, and you add, for example, the letters GIS to it. So you're looking for Mount St. Helens plus GIS, and you hit search, and you'll find geospatial layers for Mount St. Helens. If specifically you want shapefiles, you can add that. EOO is another type of file that's out there. You can look at locations like Kansas and add GIS, and you can add things like shapefiles and EOOs and any of these sorts of terms. You would be surprised at how easy it is to backdoor your way into a good data set by simply Googling what it is that you're looking for, along with the terms GIS or shapefile or geospatial data set or something of that order. Here's an example. Soils plus GIS. Lo and behold, it takes you to a lot of these things. Now, we will at some point in time, perhaps, definitely if you stay in the GIS program long enough to where you're in a class face-to-face with me, we'll probably take a look at web soil survey. And if you're interested in it, shoot me an email. I'm probably on the website somewhere. If not, I'll give you my email here real quick. It's mharman, that's MHARMAN, at nvcc.edu. And if you're interested in the web soil survey, I will be happy to make contact with you and teach you about it a little bit. It's basically a web-based GIS that serves up soils data across the entire country, along with a ton of really cool models. There's still a lot of challenges with getting data. All these sites are different. There's lots of different formats that you're dealing with, and so you got to figure out what you need to download. Some of these sites don't work the way they're supposed to, and some have no upkeep at all, and they basically they're more or less defunct, but they're still out there, and they're just they're cul-de-sacs for where your effort can be quietly led down and strangled, and you'll think you're getting somewhere only to find out that this website hasn't been updated in 15 years and there's just nothing there. The other thing that you got to remember is not all data downloads are valuable. You might download 10 or 15 things for a project, and it turns out that only 2 or 3 of them were of any practical, tangible use at all. So you're going to have to develop a fair amount of just general computer savvy to get along. Not so much with GIS, but with this aspect of GIS, because the finding, the downloading, and the extracting of spatial data is not something that we can just generally give you a good set of directions for, because there's 1,000 different ways and 1,000 different sites that you're going to be getting stuff from. They're all a little quirky, they're all a little different, and long term you need to be able to do that on your own. Now, we're not going to put you in the deep end of the pool right away with this. In GIS 200, this class, you will spend some time but looking for data, but it'll be for, you know, an at location where we know you can find it, and we will do that with the class projects, and we'll basically take you to a really good website and show you how a really good geospatial data clearinghouse should be set up and how they should function. And then as you move on to GIS 201 and other classes later on, you'll have to find your own data sources, and then the things that we're talking about here will really come to play. But this is a big one. You got to be willing to try, you got to be willing to fail, you got to be willing to explore, invent, search, and learn. GIS is not a science that is based on success. You'll learn as much in GIS from failure as you do from success. Now, ultimately, we want you to get you to where you succeed. But in order to understand that, you need to hit those potholes in the road of progress. You need to have some failure and then overcome it, because in the real world you're not going to get a set of instructions every time. You're not going to be handed the data sets that you need every time. You are going to have to learn to navigate those rabbit holes where nothing exists. You're going to have to learn how to wade into a sea of data and pull out the stuff that you need, and you're going to have to be willing to sometimes go, oh man, I can't figure out how to do this. What do I do now? No one's here to help. I don't want to look like a crazy person or whatever, and be asking for help, and everybody looks at you like you got a third eye growing in the middle of your forehead or something. No. What you want to do is be willing and able to use things like help documents, help sections on tools, Google search techniques, that kind of stuff, in order to figure out possible solutions for spatial problems that you come across. And as you do this and get better at it, you'll learn how to take a large set of tools and figure out which ones you need to use for the thing that you need to do. Zipping. There's lots of utilities out there to do this. The author here, Price, she likes the 7-zip. Windows is supposed to have some unzipping capabilities now. There are some GIS files and remote sensing that are double zipped. They're a real pain in the butt, but you won't have to deal with them for a while. But essentially, the big problem is now is Windows Explorer is capable of looking in zip folders and showing you what's there. Just because you can see what's in the zip folder in Windows Explorer doesn't mean you can access the data for your geospatial software programs. If it's in a zipped file, it has to be extracted before you can use it in ArcGIS. Scale is another one of those things that pops up all the time, and it's something that is relatively simple. It's easy to explain, but it is incredibly dynamic and important. And it's one of those things that's not going to be like this is the only time you're going to hear about scale. Scale comes up a lot. We're talking about source scale, and this is the reason why. Data can come at many scales. You need to figure out what it is before you use it for a project, and here is why. The scale matters. Scale determines the detail in features. And what I'm talking about is if you look to the right and you have this image, and you clearly see a black line, an orangish, yellowish, mustard brown line, and then a purple line. What if I told you all three of those lines were of the exact same thing, and that they're all three accurate and correct? You're probably thinking, why did I pay for this class? Clearly the guy running this program who's doing the narration for these slides is a nitwit, because there's no way. But see, that's the point. There is a way. These lines are of the same thing but at different scales. For example, the purple line of this area is at a scale of 1 to 25 million. So in other words, 1 inch on the map is 25 million inches in real time. The orange line, 1 inch on the map, is 5 million inches. The black line, 1 inch on the map, is 50,000 inches. That level of change in scale means that, for the better way of explaining it, the black line is like you're zooming in more. So as you get closer to it and you're looking at it, what you're seeing is more detail. When you look at the orange line, you're zooming out a lot further and drawing those sets of lines. When you get to the 1 to 25 million, you've zoomed out a lot. Now, in this illustration, the scale of that image is probably closer to 1 to 50,000. And so you can see the fine detail of the black line. You see how it makes it differ from the orange line. And then, lo and behold, you can see how different it would be even more from the purple line. But again, if you were to zoom out to 1 to 25 million, where the purple line is correct, you couldn't see the level of detail that's in those other lines to make those kind of things. And that's why source scale, matters. Because if you have that purple line and it's at 1 to 25 million and you're trying to do work at 1 to 50,000, you can see the purple line's not really going to work for that. But it does at the other scales, at the 1 to 25 million scale. So knowing the source scale can help you figure out whether the data set is going to be appropriate at the scale of the analysis you're doing. So when we talk about available scales, small, large, very large, and specialized. Small scale, world, country, state are relatively easy to find over large areas. Large scale, base data down to 1 to 24,000. It's common in the U.S. Very large scale, parcels. You have to find those in individual locations, like individual counties or cities. And then specialized scales. These are kind of weird, and they're like you've collected GPS points for a certain thing, and you're using just that. Now, semantics. Small scale versus large scale. Small scale maps look at very large areas. Large scale maps look at smaller areas. When we talk about large or small scale, you remember that ratio of like 1 to 50,000? That would be 1 over 50,000 versus 1 over, say, 25 million. So at 1 to 25 million, that's when you've zoomed out and you're looking at a very, very large area, because it's a very, very small fraction. And so the scale is small, the area is big. I hope that doesn't confuse you. Metadata. Metadata is data about your data. Metadata is data about your data. It contains information that you need, should be provided with the data sets, could be stored separately. A lot of times when you're downloading, looking for, or finding data, you have to download a second file if you want the metadata. Take the time when you're looking for data to see if the metadata is included, if it's separate. It's not always going to be even in the spatial stuff. It could be a link there that says, here's a PDF or a Word document, and download it and go from there. We use it to determine quality. We use it to look at these various scales, download it, and keep it with your data. Keep it in your downloads. Different styles, different standards, usually set up kind of like this. It has an item description, which is a brief set of attributes. They're quick to create, and it's a default. There's also standards-based metadata. This has a little bit more of an extended information, but you have to pick a style if you want to do this. To see more metadata, set the metadata styles and customize ArcMap options to FGDC. That's the Federal Geospatial Data Commission for North America, and it'll kind of come up with all the stuff that we require here. Document downloads, you want to always update your metadata if you change things. Price likes to put a citation in the metadata to let people know where it came from. So in other words, you download data from USGS and you modify it and do a lot of changes to it, and now it's effectively yours. You still want to credit the basic source data that you worked from, and one way to do that is to add a citation back to the original data set.